Are you using an optical chopper to modulate a laser beam and need to control the duty factor of the optically chopped beam? Hi, I'm Andy Berger with Stanford Research Systems. Maybe you have a sample that's sensitive to total input power, or you want to perform a power dependence of your sample's properties. You need a way to control the duty factor of the optically chopped beam. Today, I'll show you a couple of ways to do just that with our SR542 precision optical chopper.
Most optical chopper blades provide a 50% duty cycle waveform, passing or blocking the beam for half of every optical cycle. The simplest trick for changing the duty factor is to stack two identical chopper blades. Here I show a second blade in semi-transparent blue, so you can see that there is a relative rotation between the two blades that reduces the on fraction below 50%. By adjusting the staggering of the blades, you can set the duty anywhere between 0 and 50%, but it can be difficult to achieve a specific, precise duty factor, and any changes that you wish to make require halting your experiment and data collection. If you need a precision duty factor, we offer the variable duty factor blade shown here. Simply by choosing where along the blade radius your beam passes, you can choose a duty factor from 10 to 90%. This has a few drawbacks still. Your beam diameter is limited to about 3 millimeters. Only integer multiples of 10% are available. And if you need to adjust the duty factor, for example, in a power dependence study, your beam path must be realigned.
But you came here because maybe you already knew those tricks. What if you need continuous control of the duty factor or the ability to modify it on the fly? For that, we can synchronize two optical choppers, which is what I will demonstrate next. Here I show chopper 1 and chopper 2 powered on in their default factory configurations. I consider chopper 1 to be the primary timekeeper and leave its frequency source set to internal for simplicity, though you could just as easily select any of the other sources. I connect the source out from chopper 1 to the external sync input on chopper 2. You could also use the reference outputs, for example, the outer slot's reference output, if you are controlling the outer track to the source clock. But the chopper controller's main job is to servo the controlled track, either outer, inner, or shaft, to the source. And the blade slots will generally have a bit of excess jitter associated with them due to blade imperfections and motion control. So the source output provides a time base with slightly less jitter. Another advantage is that the source output is always available. The reference outputs are only available when the motor is running. I'll go ahead and configure chopper 2's source to external sync, and we see that it immediately indicates locked to the chopper 1 source output. In fact, if I monitor the source frequency on chopper 2 and change the internal frequency on chopper 1, we see chopper 2's PLL quickly come back into frequency and phase lock. For this demo, I have attached the standard 5/6 chopper blade to both chopper heads. This provides 6 chop periods per mechanical revolution on the outer track of blade slots and 5 chop periods on the inner track. On channel 1 of the oscilloscope, I connect chopper 1's outer slot's reference output, and on channel 2, I connect chopper 2's outer slot's reference output. These are generated by the photointerrupters at the base of each chopper head. I have arranged the beam path to be modulated by the outer track and have connected a photodiode to channel 4 of the oscilloscope. I'll go ahead and start chopper 1. We see that with a singly chopped beam, there is a phase shift between the reference output and the photodiode signal. This is because the beam and the photointerrupter are located at different positions around the blade. Next, I start chopper 2. As it comes into phase lock, we see that it has a different phase shift relative to chopper 1. This comes from differences in the orientation with which the blades are mounted on each chopper motor, and can be compensated by adjusting chopper 2's phase setting. I'll go ahead and activate a duty factor measurement on channel 4 of the oscilloscope. I'll zoom in a bit and add some signal averaging so that we get a nice stable measurement. You can see that before making any adjustments, the resulting duty factor is about 35.7%. Because of the setup-specific phase offsets, it can be difficult to predict the duty factor that you'll get for the dual chopped beam. By adjusting the phase of chopper 2, we can recover the 50% duty factor. In fact, for this setup, I need to tune the phase of chopper 2 to about 51 degrees in order to establish phase alignment between the two choppers and recover a duty factor of 50%. There is nothing special about this 51 degrees. The number will vary from setup to setup depending on the relative rotation of the mounted chopper blades. But this is why it was necessary to visualize the chop beam on the oscilloscope and tune things manually. I'll go ahead and hit rel phase to consider this orientation 0 degrees. Now, this is the cool part. With the two choppers synchronized and phase aligned in this way, adjustment of chopper 2's phase gives us a direct experimental knob on the duty factor of the dual chopped beam. Now it's as easy as turning the front panel knob, keying in a set point, or sending a remote command to control the duty factor. It's a simple leap to then use the remote commands as part of a data collection routine to perform a duty factor or power dependence sweep. It may be obvious, but I should point out that it is not possible to achieve greater than 50% duty factor with this method. If I adjust chopper 2's phase around 0 in either the positive or the negative direction, we can see the dual chopped signal decreases from 50% on either its leading edge or trailing edge. You may also not reach 50% exactly. If either blade is under-etched, then its own duty factor will be less than 50% and will be the limiting factor. For example, if I stop chopper 2 for a moment, we see that the chopper 1 blade alone provides a duty factor of 49.8%. When I restart chopper 2, we wind up with 49.7%. Pretty close. Now let's go to the opposite extreme. If I jump to 180 degrees, the two choppers become anti-aligned, blocking the signal and setting the duty factor to about 0. You can see in this arrangement a small amount of light is leaking through at the leading and trailing edges. This is due to a slight mismatch in aperture sizes between the two blades. This mismatch will set the minimum achievable duty factor. If we make small adjustments from here, we can achieve very small duty factors, on the order of 1%. As I scroll through in phase increments of 1 degree, you can see how continuous tuning of the duty factor is easily achieved with this method. Be aware that your beam size may also be reduced at small duty factors. Finally, I want to point out that the phase orientation is reproducible from run to run. For example, note the duty factor here, about 4%. If I stop chopper 2 and turn it back on, we wind up with the same duty factor we had set before. You may have noticed that for this straightforward arrangement of beam path and motors, you can use edge coincidence of the reference output signals as a rough indicator that the dual chopped beam is at 50%. In other words, the dual chopped beam is simply the logical AND of the reference outputs, plus a phase shift. However, if I change the mounting of motor 2 so that the beam passes at a different location around the blade track, you can see that this statement is no longer true. The reference outputs still appear phase aligned, but the photodiode output no longer represents the logical AND of these signals. In this case, the coincidence of the reference output rising edges is not a useful indicator of 50% duty factor, and you'll have to use the photodiode output itself while tuning chopper 2's phase. Similarly, any lateral or vertical displacements of the photo interrupters on each chopper head will shift the reference outputs, due to minute manufacturing and assembly variation, for example. so reliance on edge alignment of the reference output signals alone is never as accurate as direct measurement of the photodiode output. If your signal to noise is weak, you may not be able to visualize the chopped waveform directly on an oscilloscope. In that case, you may be using a lock-in amplifier to recover your signal. In the next video, I'll show you how to do the phase alignment between the two optical choppers when you don't have the waveform visualized on a scope and you're using only the lock-in amplifier signal. In conclusion, when it comes to control of duty factor, using two optical choppers is better than one. Because of the excellent motion control provided by the SR542, synchronizing two choppers in this way is functionally identical to mounting two blades on the same chopper motor, but you get the added benefits of high precision and repeatability and the ability to digitally control the duty factor on the fly. You can use this method with any of the blades that are compatible and offered for the SR542 in order to optimize the setup for your chop frequency and beam size. Thanks for watching. See you next time.